quantum entangled photons as because quantum entangled photons interfere with each other differently, not that like the information comes back into me. So they can use 1 or 2 photons to range rather than having to use high power signals.
Let's talk about this after class. This is a very fascinating topic, by the way. I'll tell you, I don't know what's misinformation, but I trust Adams. He actually is from Caltech, and I taught that kid undergraduate. He's pretty legit with what he says. Now, let me go ahead. You all got that velocity thing? Did you see? All right, that's just do the velocity vector's projection on the radius vector and subtract it, and then it'll give you the total top of velocity. By the way, that plane problem, the thing I had interesting was when I was looking at the position, taking the derivative of that, the velocity goes from a positive Doppler velocity to a negative Doppler velocity, and that makes sense as two cars come by each other. You're increasing sound, the noise goes down in terms of frequency. All right, now with this, what I'm going to do, I want to talk about the quadrature aspect, but what I really want to do, I want to hit this from the perspective of how you use this to do an analysis of exact range, position, and relative sigma strength. Now, you don't have to write all this down because this is in the book, but in general, we have x of t, and it's equal to, in the book, this is a standard cosine of omega naught t plus some phase angle. And they say that this is going to be the actual pulse cent. I call it p tau of t. He takes that, instead of putting it in cosine form, he puts it the real part of, and then it's going to be e to the j omega naught t times e to the j theta times a, and then times the pulse tau of t. And that means here he calls it the real part of a prime times e to the j omega naught t times p tau of t. And this is a pulse that's sent. I want to tell you what he's talking about. This is a radar. This is going to be something that is a voltage, equivalent to a voltage that's going to be scaled. Do y'all follow me on this class? He's simply saying that this pulse exists for a certain period of time, and he's just talking about a packet like this. It would be from here to here, and it would look like this. And this would be x of t. It's a voltage waveform. Think of the voltage that would go through an amplifier and drive an antenna, and that's the simplest way. So this is the thing that's sent. And then we're looking at just one pulse, one tau. We're not looking at a train. This is the thing that's sent. It's a target. He likes to use here the range R0, and hits the target, and it returns back. The return signal he calls, and I'm going to call it y of t. That's equal to this real part of t, or real part of a prime, e to the j omega naught, and then it's t minus delta t, p tau of t minus delta t. Now delta t is just the delay time, the round trip time, and he talks about this in the book. Delta t, this is the round trip time. Is simply equal to, if you think about it, it's going to be 2r over c, r0 over c. That's the idea. If that's the round trip time, then I can take a look at this term right here, over here, and I can say, well, e to the j omega naught, and it would be p minus 2r0 over c becomes e to the j omega naught t right here times e to the minus j omega naught 2r0 over c. So when I have omega naught over c times 2r0 here, I really have 2 pi times 2 time divided by c, or 2 pi times 2 times f0 divided by c times r0. And the way he puts this in the book, he puts this as 4 pi times f, or 4 pi, and then because c over f0 right here is the wavelength, you'll put 4 pi r0 over the wavelength, and that will make this signal y of t here equal to simply the real part of a prime times e to the j omega naught t times e to the minus 2r0 over lambda. And furthermore, then he's going to say it's the real part of a prime times e to the minus j 2 r naught. Kind of sloppy, 2 r naught. Or I'm sorry, this is 4 pi. 4 pi. 4 pi r naught over the wavelength times e to the j omega naught t. And it's also times the pulse, p tau, of t minus 2 r naught over c. And that's y2. And that's the return signal. And here's a statement he makes in the book that makes it important. This term right here is slowly varying. This is a high frequency term that is quickly varying. We want to actually get this information out. What we really want is that term right there. So we do, next thing is this. Oh, one other thing, this can be put in terms of a cosine format without any problem at all. You can put this as cosine, or I should say, I can put it as A times cosine of omega naught t, and it's going to be plus the phase angle minus 4 pi r naught over the wavelength. And then it would be times the pulse function, p tau, of t minus 2 r naught over c. The only reason I keep doing this pulse is because if you're going to do a MATLAB program, and you will later on, this pulse function is easy to implement in MATLAB. Instead of writing for loops and say, if this condition is true, then this, just write this and it takes care of that. And they have in MATLAB, I think it's rect, R-E-C-T, of t over tau, but you're going to have to check on that. They have a pulse function in MATLAB, and that makes it easy for computational work. So when I get down to this point, I'm really not saying too much other than what I can do is break out things that are slowly varying, this, and things that are fast, they're varying at the frequency. This is the actual carrier frequency, omega naught. Now he doesn't put omega naught in there, he puts 2 pi f naught, but there's no reason to, in my opinion. And that's the carrier frequency. Just put that in there. Omega naught is equal to 2 pi f naught, and that's the carrier frequency. Next thing that I do, now with the coherent detector, if we take this signal, and I'm going to say, I'm going to just remove this for now, just for the sake of simplifying it. We can add this back on. But now when I have a coherent detector, what I'm, write that down too. I'll tell you what I'm thinking about this. This is an oversimplification, what he has here for Q and R, really for in phase and quadrature, but it gets the basics down of what we're trying to do. And when we do this in the digital domain with sampling, there's a few things that happen that become very, very important about the timing. So this is a standard coherent detector, and it's in his book. He has an incoming signal A times cosine of omega naught t plus the phase angle minus 4 pi r naught, that's the range over lambda. It's going in, and he uses a splitter here and here. He'll take this and use a multiplier. He's going to multiply this by 2 cosine, and this is going to be of omega naught t. Then he's going to multiply this one by 2 sine of omega naught t. This drawing's in the book, by the way. He takes the output of this and puts it through a low-pass filter. Last time I said, instead of doing a standard low-pass filter, you could actually sample it at the frequency that was associated with twice actually, no, actually the frequency of omega naught. If it was f naught was the frequency, you'd sample it 1 over that f, and you could actually down sample things so that you would get baseband through a low-pass filter. Y'all remember this? This is one way to do it. Now, the output here was messing with this last night. If I take this waveform times this, and I just do, and I know one thing about this. I don't want to spend a whole lot of time on this, but I want to just make sure everybody knows this. And I want to talk about Hilbert transforms just for a second, because they fit well right here. Anytime I have x of t times a cosine of omega naught t, I've got to do this in a continuous time domain. The transform of that in a frequency domain, assuming x of t goes to x of omega, the transform of that is 1/2 times x of omega plus omega naught plus x of omega minus omega naught. I know that. If I have x of t times the sine of omega naught t, then the transform is j divided by 2 times x of omega plus omega naught, but there's a minus x of omega minus omega naught. Same magnitude, but there's a phase change. There's a 90 degrees phase change, and this becomes negative also. That's the important thing. Now, what does that actually mean? It means that the actual waveform here, the x of t goes to x of omega, will feel a 90 degrees phase change. And what that means is, when I multiply this by the cosine, the low frequency, then go through a low pass, what comes out is going to be a here, and it's going to be cosine, the low frequency components, which is going to be theta plus 4 pi r naught over lambda. And here what comes out is just a times the sine of theta, actually minus 4 pi r naught over lambda. Now, you all see, the only thing we've done is we've multiplied by these things, sine of omega naught and cosine of omega naught weighted by 2. The key things is this omega naught, because this is going to be for the received signal. You know, follow me, you transmit and you receive something, right? For now, we're assuming a stationary target. Well, that frequency has to be exactly this frequency. So when you talk about radars, the key thing from everything I know of is that you need a very stable local oscillator, which I don't know how much you know about this, but if you just take a standard LC circuit and you get a resonant frequency, if you heat that, it doesn't take much either. You will see it move. It'll move enough that you can notice it. This is a temperature variation. In your classes in electronics, did you have effects of temperature on various things like resonant frequency? When you talk about very stable local oscillators, that was the key to radar in the first place. They could amplify power. The magnetrons made radar real. Without them, I mean, we've got solid state effectively, solid state devices that could do it. And also magnetron is, again, is really something where you pulse it with electrons and it rings at a frequency, and the ring down of it feeds the actual antenna that senses things. But that ring down is precise, it doesn't change at all. Has anybody ever seen a magnetron? Do you know what I'm talking about when I say magnetron? Yeah, that's right, microwave oven. But I mean, most people don't associate with that being a critical component in radar. If you ask somebody.
Still to this day, I thought it was only early radar.
Well, I'm going to level with you. Magnetrons are cheap. You can have solid state circuits that replicate that. There's gas FETs that they use for some of this stuff. And you can even use ignitrons to do some of the pulsing. But I don't know right now what the current state of the art is for, I think it has to do with the power. Magnetrons can produce an enormous amount of power. All right. Now you have these two things, and here's the critical aspect of this. You see how R naught is right there. Now here's what I'm going to do. The book doesn't do this, but right now in your notes, if you're doing anything, put theta equals 0. The reason I want to do that, I want to eliminate that ambiguity. Frankly, theta would always effectively be set to 0. If I do that, then I get this. Then I get this. You all see what I'm talking about? Now, watch on top. What is, if cosine of minus x is the same thing as cosine of x, correct? So really, this minus can go away here. But sine of minus x is minus sine of x, correct? So I put the minus sign out here. Now that's my output input if theta is 0. I can do something. I'm gonna do it over here. Come out here and I can say that what I'll do is create a signal, and I want to do it like the book does. This is a structured signal, it'll be sampled, but for now I'm not going to sample it. I'm going to say y of t, my new output, and I'll call it y total, y sub t. It just means the complete signal is going to be actually equal to, put this low frequency signal, or low pass signal, is going to be equal to the first signal, which is going to be a cosine of just 4 pi r naught over lambda plus j a sine of 4 pi r naught over lambda, but I have to put a minus j there. Now you all see what I've done. I've created this. I'm saying this signal itself now has a value of r naught, and it has lambda naught that I know precisely, and I'm not assuming it's moving yet. Y'all follow me? This is only one pulse. And I'm saying when I take a look at this, what I can do now is say that if I have this, or I should say this divided by this, the opposite, which is minus a sine of 4 pi r naught over lambda divided by this, a times the cosine of 4 pi r naught over lambda. Now I've effectively got minus, really, the tangent of 4 pi r naught over lambda. Y'all follow me in this class? Sine over cosine is tangent, the a's cancel. Y'all agree with this? And that means I can do one thing. If I'm saying that this is now I can say that the inverse tan of that, I can go ahead and set the actual angle here, or I can say tan minus 1 of 4 pi r naught over lambda. Wait, let me do this. Okay, put minus that there, is equal to 4 pi r naught over lambda. Only thing I did, if you have tangent of theta, and you want with theta, you take the inverse tan of that argument to get theta. You all follow me, class? Now I have this with a minus sign. And now this becomes very important, because that is precise, something else I didn't say. He doesn't really go into this in the book. What he's really talking about, for one pulse goes out and back, as it comes back, when we get it at target detection, he samples that thing simultaneously. I mean, effectively, this is going to be the output of a sampled point. So we get a real and imaginary part because of that J term. Y'all follow me on this one, class? Now we can get this bit of information precisely right here. And that will be a value. And look, we can get R naught. So if I take this, multiply by lambda naught, divide by 4 pi, I get R naught. Precisely. Y'all see what I'm saying? And that is something where that range, all of a sudden, is not limited by the range resolution. Remember, range resolution was equal to c tau over 2, right? Now this can get down to something, it can be accurate to a quarter of a wavelength, but coherent processing, thing I'm not saying, this right here is a lot more complicated than made it out to be. But that's really what you're doing. You're multiplying by a sine and a cosine, a 90-degree phase change, so that you can get precisely a 90-degree phase change after it goes through the low-pass filter, and you can extract R naught. That's why this is so valuable. And I didn't say that last time. I want to make that clear. He doesn't, yeah.
Sorry.
He doesn't actually go through this in detail. Did anybody read through that section? Where he talks about Y0? He doesn't talk about how they actually achieve Y0. He just says it is a sample right at the center of the return that is associated with the tau. Now the way they get that is with a match filter. That's in chapters to come. And we use an ambiguity function to actually get the Doppler that I'm going to get to. All right, I want to make that clear. And in his book, if you're a little lost on some of that, don't feel bad.
I think it's similar for GPS too. It's been a few years since I've read up on it. So,
All right, how many have heard of the Hilbert transform? Anybody?
what?
All right, let me tell you, Hilbert transforms are used extensively for digital signal processing. And they're used for, this is a long time ago, like 1905, they needed a transform that could do this for information theory and pulling signals out. I hope I made that clear on this part of it, why quadrature is so important. Why in-phase and quadrature is so important. Now, the quadrature signal, the way it's really gotten, I show you multiplying by this, right? Say you got a cosine multiplied by sine. This is not easy to do unless you use a Hilbert transform. So here's what a Hilbert transform is. Anytime you talk about Hilbert, you can look it up. Transform. I don't know what Wikipedia has. There may be the digital form of it or the discrete form of it. There may be, this is a continuous line. Anytime you want the Hilbert transform of the signal x of t, you simply convolve it with the function 1 over pi t. That will give you a 90-degree phase shift. You follow me? So this is actually the Hilbert transform of x of t. And they'll put it like that. Now why is that important? Here's what the Hilbert transform does. It changes it by exactly 90 degrees. So the cosine, when you turn into a sine, you see how that minus sign comes out? This component is usually gotten by taking the negative of the Hilbert transform of this right here. That's how they actually get it. So what does the Hilbert transform look like? That's another good question. Technically, if you remember convolution, it's the integral. This is a continuous time, unfortunately. It's an infinite length signal. When we get to digital, where we're going, we're going to take it for a finite digital series and show you how to do it. But right now, continuous time gives you a peak. From infinity to minus infinity of x of t, whatever x of t is. Now, if you do convolution, what happens? Well, the pi comes out in front, right? Instead of t, it's t minus. This would be, not t, would be tau, right? And then it would be 1 over, and this would be t minus tau, d tau. That is the definition of the Hilbert transform. Alex, are you looking on Wikipedia by any chance?
That's what Wikipedia says.
What?
That right there is on Wikipedia.
This is the continuous time form.
Yeah.
Problem is, it doesn't give you the real insight. You'll notice how it goes from minus infinity to infinity. We can't go there. We'll always do our processing in discrete time. But this gives you a glimpse of it. Now, here's the trouble with this. Y'all notice that there's one thing very odd. What happens when t goes to tau right here? It's a singularity, right? So there's a thing called, I think it's the prime value of the function. There's ways to extract that information. Normally what they do for a Hilbert transform, by the way, when they're teaching analog, they go from minus infinity right up to the point where this thing goes to an impulse. And then they go from the impulse all the way just on the other side of it out to infinity. And then they add that point where it's going to infinity. Now, you gotta understand something. If this is still finite, when this goes to 0, then you have an infinite amount. So what they do is make sure that this point right here, when this happens, this is gonna be at a 0, it's tending to 0. And there's tricks to this. Y'all follow me? The only thing a Hilbert transform really does, if you're looking on Wikipedia, it says it adds a 90-degree phase shift to the wing. So it means if you had that cosine up there, you would get a sine. And frankly, I want to level with you, the Hilbert transform operation can be done up here, but it requires an enormous amount of data, so it's usually done right here.
I think it subtracts 90 degrees.
Yeah, I'm sorry. It subtracts 90, but that one is actually, that side is actually the negative of the Hilbert transform of the signal, the in-phase signal. But here's the real thing too. You'll notice to do this, I don't need a second stable local oscillator. I mean, I don't need to do something where I get a time shift right here. I mean, to do this phasing is very, very hard. When to get a cosine and a sine just off by a quarter, I mean, literally by 90 degrees, they do it with delay lines usually. You know what a delay line is? That's typically what they do. But the problem with all this is that local oscillators, as stable as it may be, wobbles. And then whenever you get wobbling, it's not a quarter wave. It's not pi over 2, sorry, at 90 degrees phase. That'll change, and that little bit of phase change disrupts signal processing. So please keep in mind, it's so important to make sure you have exactly that pi over 2 phase change.
Does it change it by a lot? You know
Well,
what I mean, like,
Let me level with you, all right? I have not done any kind of studies where I've taken a look at the actual total effect, but I know this much. From everything I've done, when they're talking about how stable does a stable local oscillator have to be, and for this phase change, does it have to be exactly 9 degrees difference, or can it be like 89.999? The percentage error in here is like 1 millionth. I mean, they're talking about parts per million difference if in the total frequency of these two with the exact 90 degrees phase change. And there's a lot written on this. I've got a paper right here. Oh, by the way, these are your quizzes. Sorry I didn't get back to you. Let's hoping everybody got here. Chase. Thomas is in here. Will. Mandy. It wasn't meant to be hard. And I think I put the solutions online, but I don't know if they're not on there?
I'll check.
Well, I've got them, I got them in a different notebook, and Garcia's under it. So that's sort of my quadrature crossing is important. Now,
I don't see that they
if not, I've got it in a notebook, I have tests and quizzes for this class, I've got it there, I didn't paste it into the right section, but I'll put them there. If you give me, right after class, if you remind me, I'll do it. Not that you need them, because this, I think did we go over this or not?
we went over basically everything.
I think it's easy, but some people have questions. Now, look, the next thing I'm talking about is range bands. He talks about this, I'm gonna try to do this in a way that'll make it understandable. And the way I try to structure these lectures, if I'm sitting where you are, what do I need to know? Not what, what does the professor wanna do with a bunch of PowerPoints that are really beautiful to look at? But what do you wanna know? Well, you wanna know, first of all, how to deal with problems. Second of all, what's really important in the real world. In my working with radars, I was at NASA, I had to do a critical evaluation of a radar system that had an embedded signal. I've done other radar work. I've never built a radar from scratch, but I was part of projects with people that had built radars from scratch. The current research I'm doing with radar is twofold. One is, I'm working with another kid named Luke, and we're trying to get to eliminate both not ambiguous range and ambiguous Doppler, so having no limit to the Doppler frequency or to range. And we're writing a paper about to send it on this. Signal processing is something I'm doing a fair amount of. Now, one of the things that I'm very, very aware of, and I think everybody should be, is when you're talking about this data, you've got to store it. So we're going to jump, and this is sad, we're going to jump from continuous time to think like discrete time, even though we're not going to be discrete time. Let me explain something. So when I send a signal, you don't need to write this down, this is a radar. I've got a target out here at a range R0. It goes out, it hits, it comes back. I know what I'm going to see basically is going to be delayed by 2 times R divided by C, correct? I know that. Now, when it's coming back here, there's a term that's used, range bins. These are not Doppler bins, these are range bins. And here's what's happening. I send the signal out as soon as this part of the signal is done. Once I'm at this point, right here, call this time. Now I start listening all through here. And as I listen, I do this. I create a bunch of bins. If this is time, this is in the range where I'm listening. All right. And these bins, you can all follow me on this, are going to have a width of about tau. Actually, it should be less than tau, but I'm going to say they're tau. This is a range bin. What happens is this. If, when I'm listening, we get this signal, but this is versus time, this is x of t to transmit, and this is y of t to receive, I'm going to have a delay to here, and then I'm listening. And then all of a sudden, at some point, I'm effectively going to get something like this. And I'm taking all the noise out, but I'm going to get targets that are noticeable. Something where I can say, yes, it's above a noise threshold, I've got targets. So there's none there, then I have a target. A target has an amplitude A1. Then none, another target, amplitude A2. Y'all follow me on this? These are the range bins here. Each range bin is with tau. Now think about the distance it corresponds to. That corresponds to tau c over 2, right? That would be the actual distance, right? Now when I'm looking at this, I can say, well, there's a target here, here, and I can look down here and see how far away it is. Now, something I also have to tell you, because that's the width, I have to also add on the actual, because remember, this is the end of transmission, now I'm listening, I have to take in the effective tau right here. But this is what's done. And the way they store range bins is this way. And it's just a mental picture. Usually they say this. This is the first range bin, and this is called fast time. And this is really, the width of this is the PRI or T. That's the fast time on this axis. And the only thing that's happening here is now, if you can see, this is the first range thing I'm saying, is that what I have is this. I have a whole bunch of range bins here, and I'm identifying where a target is. Let's say A1, A2. Now that's the first pulse that goes back. It's one PRI, I mean, it's just a PRI on. The next pulse that goes back is going to have the same thing. It's shown in the book. Let me give you the page number. It's figure 813, if you could find that. If you got a copy of the book. And here, I'll show you where it is. But I need to tell you, this is important. Remember, this gives you a mental picture of what you're doing. That makes it easy too, by the way, to do this stuff. Relatively easy. We try to Fortran code for this stuff. You all wrote C code, right? Well, in my opinion, the difference in writing C code to do something using MATLAB is MATLAB is so much easier.
Depends on what you're doing.
There are things between C and MATLAB.
It's like comparing apples to oranges.
Well, to tell you, this is something we do. We take Fortran code, we take MATLAB as our prototype, and we can literally down convert it to Fortran 9. It's object-based. I know you can do it to C too, but microcontrollers, to this day, they use C as the standard for programming. Well, I hate writing in C. I mean, I've never really written C. I hate writing Fortran when I can do it in a higher level language like MATLAB, or you guys use Python, and I'm trying to learn Python. So let me just show you.
Fortran is a very different beast from C, I would say.
What's that?
Fortran is a very different beast from C. Fortran is painful to write for everybody that writes it.
Fortran 9?
Yeah.
Well, you do have to format, and you have the first 6 columns, first 6 spaces is just for comments, and there's a lot of different things.
Yeah.
But C still requires formatting, doesn't it?
No.
It has no,
You can write C all in a single line, and it's more than happy to parse it.
well, I'm not a C guy, but I appreciate that comment. Figure out, look at my range bins, figure 813, 5. Okay, here's what I'm talking about. The way they're doing it, there is the one on page 290 where it shows a single range bin. It's just storing information, and each one of those things is a width tau. Now, actually, normally they sample at least 1/2 tau. Normally, just to make sure that they don't miss the target, or faster, and they store them in range bins. Then they build this. So down here, you're going to have, if I can do this right, you're going to have this. And it's just for data storage purposes, so you get your mind. This is all, by the way, this is looking at just one target, one azimuth and elevation. So this is not at multiple targets, but they'll have this. And you'll see these drawn all the time. And you'll have however many range bins there are. Typically it's 20 or more. And then they'll have this. You all know what I'm doing here. I'm basically parsing this thing. And then, basically you're going to have a row. This is slow time, write that down. And this is fast time. And this is the PRI right here. This is the full length of the PRI. The width of this is at least tau times C over 2. Usually it's smaller than that, but that gives you the actual range. Follow me on this? Now, think about this. Here's pulse 1, 2, all the way till we have pulse N, where this is now a dwell time. that's only looking at one point. So normally what you have is, you see I have a 2 by 2 here, right? So I'm gonna have a vector for range bin, RB, and it's gonna be indexed, call it IJ. So now I can say for any IJ, I might be the fast time, J would be the slow time, right? You can say for maybe the third pulse, a target appeared, but it didn't appear here, so we can get into the probabilistic of how likely is there a target there. You follow me? It's still looking at only one point. Then there's an added thing that happens, and this is shown in there. A lot of times, what they have with antenna, array antennas especially, they'll have not one point, but they'll have 3 phase points or more that they choose from. So they're gonna have 3 receivers or 3 effective listening devices. And they literally connect the array in different ways, and they get 3 different points, all looking at one azimuth and elevation. And then what you'll see down here is this repeated several times. And this will be for the first antennas, the way they have the antenna configured. This will be for the second and third. Now, in the book, he talks about this. Typically, when you have antenna arrays, you have subarrays, and you will do what's called the sum of the 2 subarrays and the difference in the 2 subarrays listing. And then you're going to have something where there could be either a multiplication of the 2 or quadrature, effective real and imaginary part added together to see if there is a target or not. There's a lot, this is more of the signal processing that's downfield, but just be aware of that. That's just for one azimuth elevation, for one dwell time, okay? You gotta store this. Now typically what they do here is, if I have an R, this is a range bin, I, comma, J, then they start putting on other identifiers. Now that's for any given azimuth and elevation. So then they'll add N, K, or M, or K, sorry, K, comma, M, or KL, comma, M. And what this will be is for any azimuth elevation, you'll have that. The M will actually keep track of how many times you actually go ahead and do a search. Do y'all follow me on this? Because you got a frame search. Frame search is when you search the area 1 time. And would be 2 if you search it 2 times. And they're populating this space. And you'll notice it's not 2-dimensional or 3-dimensional. It's n-dimensional space. And one thing about MATLAB I like, you can put a vector, you can create a matrices that's got, it can have both length, width, height, effectively time, and any other dimension you want to add on. So you can have spaces, instead of like a 2 by 2, you can have a 2 by 3 by 5 by 7 by 9, and MATLAB will allow you to do that, so you can store this information easily and extract it. Y'all follow me? So here's what we're kind of going. I'm going to go ahead and just pretend now, I'm going to go ahead and interrogate space with a search, with just a search, right? And I'm going to have, forget the multiple phase fronts, I have only one receiver. In there, I'm listening, I'm going to go for a dwell before I move on, go for a dwell, move on, move on, move on. All this data has to be stored. Can you all see that this is becoming a data-intense problem? Because we have to store all that data, then we have to repopulate that, create a new data, a new frame to populate, and we have to start doing signal processing on it in real time over a small length of time. We don't have the luxury of just recording all this and then go back into the lab and saying, well, maybe there is a target or isn't a target. Now we have a data, basically strip charts data. We don't have that with radar work. It has to be real-time decisions. That's where the problems come in. But I hope I at least make you appreciate the problem. It's a lot of data, and you got to do processing on it too. So just keep that in mind. But the data cube gives you a mental picture. That's why he's talking about. The next thing I have to talk about, and this is very simple coherency. This is on his page 293. He's trying to make a point of what coherent signal processing means. And I'll tell you, I read that book many times. I've read other books. Where you really see how coherent signal processing works is when you actually write your first algorithm, with and without coherent signal processing, and then it's clear. But here's what it basically boils down to. You're going to have a very stable local oscillator. I'm going to draw it like this. Now, he does, I've got that drawn there, this is on the top of page 293. What he's trying to do is say, what I want to do is have a pulse turn on here, turn off here. So up above, this is going to be my transient, my X of t. This will be when it's coherent. And it will turn on here. Turn off there. Comes down, right here, turns on. And what I'm trying to show you is this. I'm saying, when I turn this pulse on, and when I turn this pulse on, they start at the same phase point right here, typically at a 0. Y'all follow me on that? It's at a no. That's coherent. It's a coherent wave. I sent it. This would be associated with T, or the PRI. This would be associated with tau. And this one looks identical to this one in every way, shape, or form, right? Now, and by the way, I'm exaggerating. There's a whole lot of pulses here. There may be 1,000, 10,000, maybe 100,000 pulses in this tau, all right? But they both start at a null, and they're the exact same signature. And he talks about, well, this will have an amplitude A1 of T here, and this will have an amplitude A2 of T. Don't worry about the amplitude, just follow me on the pulses. Here's non-coherent. What would happen is this. This pulse would come out fine. All right, it's going to be fine. This pulse, when it starts, will start at a peak. In other words, now it's not coherent. It didn't start at a null. It's not the exact replica of this. There's some phase difference. Y'all follow me in this class? Now the width here will be the same. All right, but because the phase is different, now when you capture this one back, you can't do coherent signal processing on it. Because remember, I multiplied by the sine of omega naught t and the cosine of omega naught t. That's assuming it's synced perfectly. And I also assume that the theta was 0, right, because it complicates things. Y'all follow me on this class? This is important. At least you get a glimpse of this stuff. So, now for Doppler in this chapter.
Dr. Radinsky, so omega naught is,
2
what
pi
is
f
it?
naught.
Right, is that associated with the carrier or
Yes.
with the message? Okay.
No. Anytime you see omega naught, as far as we're concerned, that's the carrier frequency. All right. T it has to do with the actual repetition rate of the PRI, and then tau is just the width. By the way, there's a lot we're going to talk about. We're going to talk about how this radar signal will not have the same frequency. It's called chirp. What it'll do is start at some F naught. By the end of the PRI, it'll be at some F naught plus delta F. It'll sweep in frequency. Chirping is what it's called. You've heard of this probably. It allows a much more clear, it gives range resolution more defined and targets more visible, but the signal processing is much harder. Think about that. Now you're changing the local oscillator's frequency. And you have to keep tabs on exactly when you do it. It's a very bigger problem.
I just built an oscillator like that on Friday.
Chirp oscillator?
And not intentionally, but it's funny that you just mentioned that.
Well, we're going to get to a lot of the reasons for it later. So now, this is Doppler signal processing. And this is, again, in terms of modulated, high frequency pulses modulated, not baseband, so it's important. So this is Doppler. When I talk about Doppler processing, I first have to create the scenario of a radar here. I've got a target at a range R0 here. Got this here, and I'm assuming it has a velocity in the radial direction of the actual radar. And again, you're sending out information, it hits, then you have information coming back to you. Right? So you got a round trip thing. When I do this, I'm going to say that in my baseband signal, this is baseband, here, but an individual pulse will be labeled with small n. So that's the baseband. That's gonna be multiplied by a high frequency signal. When I talk about the phase shift, please follow me on this. This is gonna be the phase shift. This is where it gets important. All right, first, what do I mean by phase shift? It's the phase shift that occurs when you go out and back. So, we've done this before. We know 2R0 is actually the distance traveled, right? 2R0 by lambda is now the number of wavelengths that the actual signal traveled. It hit and came back. Do you agree? I'm trying to be real simple with this. And we know if we want the total phase change in radians, we multiply this by 2 pi. Or now we get 4 pi R0 divided by lambda. And this is the phase change that occurs as the wave transgresses, right? Or moves through space. Now, the actual phase change that happens when, and the actual phase change that happens, or the change in phase that happens over the duration of this pulse is this, I should say for any point in pulse. Now we're going to get 4 pi, this is the phase change over the duration of pulse, and that's going to be 4 pi over lambda. But now it's going to be R0 here, and it's minus m times t, the PRI times V. Let me explain this. You realize the PRI is, I'm putting down as t. That's the length of time. So as this object is moving, from the very first instance it hits, it would be at R0. But now, every time I talk about another pulse being sent, well, now there's going to be a phase difference, or a lowering of the phase, a reduction by MTV. At the very end of it, right, when M pulse is capital M, the total phase change would be capital MT times V. Do you all agree with that? Do y'all follow me on this class? Now let's put this into the equation. That would be how much phase, this is the phase change for the pulse M. This is the initial phase change, just 4 pi R0 over lambda. And you all know how I got that, right? R0, 2 R0 is the distance traveled, divided by lambda, that's the number of wavelengths, then multiplied by 2 pi, that's the number of phase, the amount of phase change in the waves. It goes out and comes back. But that amount of phase is reduced because as it's coming at it, now the range is reduced. It's not R0 anymore, it's R0 minus MTV. You follow? That would be R right there. You know, it's in the radial velocity. So what does that do to the waveform? This is where it gets interesting. Now, before I had Y, and I'm going to call it Y of M for a reason. That was equal to A right here, and it was times the real part, he likes doing this real part stuff, real part of A, actually, times EXP, and this would be to the J, this is going to be low frequency signal, by the way, low frequency signal. After low pass filter. EXP to the J, and then he's going to leave the phase angle in here, minus 4 pi over lambda, and now it's going to be R minus M times T times velocity in the radial direction. Are you with me on this one? This will make sense in a second. What I'm really trying to say is, you know, I had a real and imaginary part coming out of that one, right? I had the cosine, and I had J sine. Well, that is the exponential, isn't it? By that I mean this, if I have e to the J anything, that's equal to cosine of anything plus J sine of anything, right? Do you remember how there was a cosine here of just effectively 4 pi R0 over lambda? And then this was a minus J sine, let me put it this way, minus J sine of 4 pi over R0 over lambda. Do you all remember that? Well, isn't that just the exponential? So here I can do this. And actually, I can put the minus on there to make sure it's right. Now, when I look at this, I can see something that happens. I'm gonna just take a look at this part right here. I have 4 pi, this would be R naught over lambda, that's the initial phase change. But now I have minus, and it's gonna be 4 pi over lambda times t. I'm gonna put times VR times t. And here's what happens right here. What they do is break this out so it looks like a Doppler velocity. Well, when I take a look at this, or Doppler frequency, what is the Doppler frequency? Isn't F Doppler just 2v over lambda, right? So what they do here is they're gonna leave a 2 pi out in front. And now I have 2v over lambda, and that is F Doppler times t. So now I can say that this expression, y of m, in other words, this is the y that would be associated, this is a return for the mth pulse. Y'all with me on this? Now that's going to be equal to, and this is the low pass filtered version, by the way. Get rid of that A. It's going to be the real part of A exp, the minus the quantity of theta minus 4 pi R naught over lambda naught, and then it's going to be plus, because it's this minus that, plus 2 pi F Doppler times the period t. With me on this, guys? Now, the thing about it is, let's let theta be 0 for the sake of simplicity. Now I have this, makes that positive, and this negative, right? Remember, this is going to be this is through the low pass filter. We have the real and the J, we have the cosine of this, right? And we have J sine of that. You all with me on this, class? So now, if we have that, we can actually get the Doppler velocity out of this. Now we can say this, and this is kind of important. When I look at this, this is what comes out of the low pass filter, and what this is really what? It's y in phase of m plus jy quadrature of m. That's what this is right here. Everybody with me? So, if I look at this, I know the real part of this, I'm sorry, not the real part. That's actually what I should have. My bad. This should just be a e to the 4 pi r naught over lambda naught minus 2 pi f Doppler t. And the exponential form takes care of the real and imaginary part. This. Now I can say that if I want the actual Doppler frequency here, because I've got the real and imaginary, I can say that 10 to the minus 1 of y quadrature of m over y in phase of m here is going to be an angle. And that angle is going to be 4 pi r naught divided by lambda minus 2 pi f Doppler times t. That's the available information. Now why is that important? Because this range R naught right here is going to be the same for every given value of m. Y'all follow? 2 pi f Doppler, and it's times in this f Doppler right here. I neglected to put the m there. Pardon me. There should be an m right here.
Oh, yeah, I was wondering about that.
So this is going to be 2 pi f Doppler times m. My bad. Put that back in there. And this is the reason I'm saying this. Because look, you're going to get this measured, right? As we're sampling, every time we're going to get this. There's one thing that's going to be consistent, this. But the difference from here to here will be an increment on that. So you can actually extract it. Y'all follow me? If this is for m equals 1, for m equals 2, it's still 4 pi r naught over lambda naught, minus, and then it was 2, would be 4 pi f Doppler times t. This would be just 1 if it was m equals 1. And you can extract the Doppler by the change. So the change in that is going to be actually equal to 2 pi times f, 2 pi, it's 2 pi f Doppler t, and you can divide by 2 pi, or 2 pi t and get f Doppler. Now we're going to spend more time on that later, but that's the essence of how you get Doppler frequencies. All right? You actually have to do this and realize the change in the actual range position will be felt as an effective Doppler frequency. This is in your book. I didn't do that as well as I wanted to because I know the digital signal processing part of the course is really going to bring this out hopefully. But I want to talk to you next about how this information appears. And this is all in that chapter. Now, we talked about clutter, and we'll spend a little more time on that. But really, this is what happens when you're looking at the way they display data. Write this down, by the way. That's 0. This is minus PRF over 2, and plus a PRF over 2. That's the maximum, actually the maximum spread. Because after that, any frequency we see up here is an ambiguous frequency. Y'all follow me on this? This is Doppler frequency. Now what they do is basically create a region right here where it's a no-go zone. What that is, this is 1 over T dwell. That's the Doppler. What that is actually something that's the ambiguous Doppler frequency. Do y'all follow me in this class? They'll just gray this out. But then they'll do this. They'll have a whole bunch of range, and each of these is associated with tau and time, and you can normalize that to range. They're going to have this, and this is the Doppler frequency. So as you go down, you send out information, it comes back. Then you extract to see if there's a Doppler shift in the size of the actual strength of the return. And if there is, what you'll see is you might have a target here, then you might have a target here, and a target here. And that's displayed in the book. I can find the page. On the bottom of page 295. If you look there, what he's trying to do is give you a picture, and this is for just one, this is only one range bin. Follow me? It's literally, we're sending out one dwell time. I mean, it's just one going out, one pulse, one PRI going out, coming back, and now we're seeing within that one pulse where the actual targets are. Now the next pulse that goes out, we're going to see targets. We may or may not see these. If we see the same target, we're getting a more confident look at it. We send it out again. Remember, we're going to keep on the azimuth and elevation at that target in that area for a total of a dwell, right? We're going to keep sending it out. So over the course of a dwell, if you have many, many targets there, but maybe not many here, it doesn't show up in everything, then you're very confident about that, but you're not confident about this. Y'all follow me on this? This is sort of how we're going to be going through this. This will get real quantified a little later with the digital signal processing. What he's trying to do in this chapter is give you a visual idea of what's going on, sort of a picture, mental picture. That's what has to be done with all the processing. The information that's actually going to come back to the radar operator is going to be a 2 or possibly even a 3D projection of the region with targets that are known targets being identified one way, usually with some, maybe a very white or blue symbol. Targets that are possible targets with a reddish symbol or something like that, where the color and the location it actually distinguishes. Now, has anybody ever seen an old legacy radar? You've seen them in movies where they have literally a CRT, and they'll have some electron beam moving around, right? And then whenever there's a target, there's just a blip. I've actually worked with one of those. It was a 48, I think. And you're looking, it's a long, or 49, it's a long-range radar, navigational radar, and there's ships that get a blip. There's not much difference between the ship the size of a carrier and an oil tanker. It didn't have any way of really telling me how large a return was. This is a World War II radar. Modern radars do. Modern radars, the displays are very, very important, and they give you information about not only the size, relative size, but the velocity of the target. We talked a lot about Doppler, right? Well, Doppler is very useful, but what positional radars do is locate where targets are in many frames or many dwell times, and then they get a velocity vector, a true vector sense of where the velocity of the target. Because you can have something coming this way that's going maybe Mach 3, the actual velocity with respect to you when it's perpendicular right here is 0. But yet is on your radar, it's picking up the position and the trailing points, and it can actually determine the actual velocity of the target. That's important. All right, then the clutter on the ground. I did this last time. The page is 297 in the book. I'm not going to spend but a second on it, really. And I got to mention this. And then, actually, what do I have? Let me ask you this. Did most of you look at page 297? This is the plane flying, and it's got an actual main lobe of clutter, and it's got a center point, and then it's got the actual width of the velocity space. Did you all look at that or not? Tanner?
I did not necessarily.
No? You remember me doing this in class?
Yes.
Would you please look at this? I don't want to spend any time on this right now because this is fairly straightforward. It's a simple formula to actually get the bandwidth or the, I call it the bandwidth. It's really the width and the frequency domain of the top of the Doppler clutter. And Doppler clutter, he gives you a picture. It always is a big, if you're moving, if your radar's moving now. So it's like a police car or an aircraft and you got looking down on the ground. Then you always get a clutter signature that'll be off a certain amount. And it's very, very predictable because that velocity, because of the angle of your radar, you can actually see it comes from your velocity. And there's ways of doing this that we'll get into. But what I want to talk about now is going to the digital, or discrete domain. We'll get into quantization too, but this is going to be chapter 14 stuff. And this is where the course gets really interesting. So before we had x of t goes to x of omega in the continuous time space, right? And we know that x of omega here was equal to the integral from minus infinity to infinity of x of t times e to the minus j omega t dt. And that was it. There was no ambiguity about that. If we had a periodic sequence, if we had x of t and it was periodic, and I did this, when we take a look at what happens over here, if it's periodic, right? We took the infinite beta nails, right, and we turned it into a Fourier series, right? And then we turned it from that Fourier series, we got the frequency shift. We noticed that over here, what happens if I have a beta nails here? Better yet, if we have x of t right here, and it's periodic, then what you end up getting as a Fourier series, this is going to be a periodic series here, periodic. Where n goes from minus infinity to infinity, and I'll call it c of n times e to the j n omega naught t. And c of n can be found as 1 over t, the integral over a period from minus t over 2 to t over 2 of the signal x of t times e to the minus j n omega naught t dt. Y'all remember that, right? That's standard Fourier series analysis, correct, class? All right, usually we do a cosine series thing. Then we did something where we took x of t, right? And it could be a chaotic or it could be non-chaotic and periodic. X of t, and we took this and we multiplied by beta nails, and that's going to be n equals minus infinity to infinity of delta of t minus nt. So now this is going to be x sampled, right? And we saw, if we think about continuous time and what it's viewed as, then it comes over here as what? Now we're going to get 1/2 times, and when we do this, I think you remember this, it's actually, we do this way. It's actually going to be an infinite series now. And you can use k if you want, from minus infinity to infinity of x of omega minus k omega sampling, the sampling frequency, and you have 1 over t out here. And I can say that this T is the PRI, and it's equal to 1 over the actual sampling frequency. And this would be the sampling frequency, right? Omega S here will be equal to 2 pi Fs. Y'all remember doing this? The only thing I'm saying is when you sample a signal, it basically takes that signal's Fourier transform and it spreads it out over the band every omega naught. Just same thing, it scales it by 1 over T, right? Or multiplies it by the PRF, pulse repetition frequency. Those are things we've covered. This is all important. Then we did one other thing, I'm not going to do it right here, but we took this and we multiplied it by a simple pulse function of width dwell time, right? So now we had an actual series, continuous time series of a radar dwell time, right? With all those PRS, correct, class? Now what we're going to do is this. Now we're getting into the discrete domain. I'm not quite over yet. So now instead of a Fourier transform or Fourier series analysis, I'm going to do this. I'm going to say now instead of x of omega, we're going to have x of capital omega. And this is called the DTFT. And that's going to be equal to the integral. Well, actually, it's not an integral. Before, remember, x of omega was equal to the integral from minus infinity to infinity, from minus infinity to infinity of x of t times e to the minus j omega t dt, right? Plus j. That was equal to x of omega, correct? That's the Fourier transform definition, right? The DTFT is really the sampled version of this. I'm out of time to prove this, but I just want to put it down. The DTFT is from n equals minus infinity to infinity of x of n. Now, x of n is a sampled signal, and I didn't have time to really get through this, but you've had signals and systems, right? X of n is now a sampled signal value. And instead of having this, you have e to the j n capital omega. Instead of an integral, you have a sum. Instead of small omega, we use capital omega. Here, I've got to tell you one thing. Whatever this is, it repeats itself every 2 pi. That's the one thing about the DTFT you have to know. It repeats itself naturally every 2 pi because it's sampled. Anything you have that's sampled repeats itself. Now, I'm going to get to chapter 14, and I didn't have time to get to it today, but I wanted to go through the essence of what you need to be aware of in chapter 9, or chapter 8, pardon me, and I gave you some problems, right? In the end of chapter 8 that we're doing. None of them were tough. Did anybody have any difficulty at all? Huh?